Hello friends, in the last part we have discussed about magnetic field intensity. In this part we will start from that point and we will discuss the magnetic circuits. So it was assumed that the magnetic field was uniform. So the integral of H dot dl is equal to H times L. Now the magnetic field intensity is a description of magnetic field in which the effect of material is not considered. But if we would like to consider the property of material, the magnetic field can be described by another quantity, that is flux density B, and B is related to H by B equal to mu times H, where mu is called the permeability of the material. The permeability of free space is equal to 4 pi into 10 raised to power minus 7 Henry per meter, and it is denoted by mu naught. The ratio of permeability of a material and the permeability of free space is denoted by mu r. So mu r is nothing but ratio of the permeability of the material and permeability of free space. So we can say mu is equal to mu r mu naught. Therefore we can say B equal to mu naught mu r H. Here mu r is called relative permeability of the core and H is magnetic field intensity. The typical range of mu r for a magnetic material is something like 10 raised to power 3 to 10 raised to power 5. If you consider the Ampere's law, which we have discussed in the previous part, the magnetic field intensity H, that is decided by current enclosed by the loop and number of turns. It is proportional to current, and the current can be considered as an independent input, or we can say the magnetic field intensity, that is an independent input to the magnetic core, and the output or the dependent variable will be the flux density, which depends on the material property. That is why when we talk about the curve between B and H, so we call that BH curve. We use H variable in x-axis and B variable in y-axis. The flux density depends on mu and H, both. The unit of flux density B is Tesla, or we can write it as Weber per meter square. Now let's focus on mu r. What does it represent? Mu r is the indication of how permeable the material is compared to air or free space. Now let us consider a magnetic core with relative permeability of 5000. So we can say mu r is equal to 5000. It means that the material of the core is 5000 times more permeable than the free space. In other words, the same current or magnetic field intensity will produce 5000 times more flux density in the magnetic material compared to the case of the free space. Now, high flux density can be produced by same current in a material with high permeability. That's why these magnetic materials of high permeability are used for electric machines cores. Now let us consider this BH curve, which is shown in this figure. Here I am showing two lines. So what is the slope of each line? The slope of each line is mu, the permeability of that particular material. Here I am showing two lines, 1 and 2. So the slope of line 2 is high compared to 1. It means to get the same flux density B, we need less magnetic field intensity for material 2 compared to 1. So that is why we have considered the path in the Ampere's law slide inside the core, because this is the highly permeable material. So if let's say, for example, let's take this path. Okay, so in this path is also enclosing the same current which is enclosed by this dotted path. Okay, however, the permeability of the path from here to here, this length, the permeability is of free space, and the permeability from here inside the core, that is the permeability of the magnetic material, which is 5000 times higher than the free space. So the flux inside this core is 5000 times higher than the flux in the air, or in other words, the flux in air gap is 5000 times less than the flux inside the magnetic material, which can be neglected. So that is why we only focus on this path, because this is the path where the magnetic field or magnetic flux density or magnetic flux exists. Till now we have discussed the relationship between H and current, magnetic field intensity H and current, that is H equal to Ni divided by L, and the relationship between flux density and magnetic field intensity B equal to mu H. Now let us combine these two. So we can write B is equal to mu naught mu R Ni by L. Now the flux density B is defined as flux per unit area, and the unit of flux is Weber, and it is denoted by phi. So phi is flux, and phi is nothing but B times A, flux density multiplied by area. A is area of cross section across which the flux is considered. In the previous slide, the area of cross section is shown like this. So this is the area of cross section. Now using phi equal to BA and B equal to mu naught mu R Ni by L, we can say phi is nothing but mu naught mu R Ni by L times A, or we can combine these things and write mu naught mu R A divided by L multiplied by Ni. Why did we do so? Because if you look at mu naught mu R A by L, all the quantities in this expression are either constant or fixed for a particular core material and shape. Mu naught is a constant, mu R depends on the material of the core, A, area of cross section, and L, length of the path where magnetic field exists. These two, they depend on core geometry. So this term mu naught mu R A by L is used to define a new variable which depends on a particular core or material, and that new variable is reluctance, and reluctance is given by L divided by mu naught mu R A. So if we have chosen a core, then mu naught mu R A L, all these quantities are fixed for that particular core, and then we can define using these variables reluctance for that particular core and core material. Using this and this, we can say flux is nothing but Ni divided by reluctance. Here Ni depends on the current, and it is like a input given by the user. So it is an independent quantity. And this Ni is referred to as magnetomotive force, MMF. So we can say the flux is nothing but MMF divided by reluctance. This is analogous to current is equal to voltage divided by resistance in an electrical circuit. So from these two we can say that MMF is analogous to voltage, flux is analogous to current, and reluctance is analogous to resistance. Now MMF depends on the current input by the user. Reluctance depends on magnetic core and its material. Now if let's say a material has very high mu r, so if the mu r is very high, reluctance becomes very small. So for the small amount of current we can get a desired phi. Just like if the resistance is small, for a small amount of voltage we can get a desired current. So highly permeable material offers a low reluctance. An important point to note here is that this I and this I, please do not get confused with these two I. This I, which is used in the calculation of flux, is the input to the core as shown here in this circuit. However, this is the response of a resistive circuit due to applied voltage. The circuit can be like this. So this is applied voltage, this is the resistance, and this is the output current because of the applied voltage. Now the current is flowing from positive terminal to negative terminal outside the voltage source. However, inside the voltage source it flows from negative to positive terminal. Now let us use this convention and the analogy between electrical and magnetic variables and try to draw equivalent magnetic circuit for this. The MMF is Ni, and then we have reluctance R, which includes the reluctance of the core and the air gap. The direction of flux is given by right hand screw rule, and that we have shown that the direction of flux is this. So let us say this is the direction of flux. So what will be the sign for the MMF? Now inside the source, the flux will flow from negative to positive. So this should be the convention for the MMF. And outside the source, the flux flows from positive to negative. So using this convention, we can draw an equivalent magnetic circuit. Now there is one more convention which we have to understand before we complete the topic of magnetic circuit. That concerns the visualization of this circuit as a magnet. Here what we are doing, here we are applying a current and getting the magnetic field. So if we have something which generates a magnetic field, then we can call it as a magnet. But here we are generating the magnet from the electrical current, so we call this electromagnet. So if we have a permanent magnet, so we will have two poles, north and south. What will be the flux lines? Inside the magnet, the flux will flow from south to north. However, outside the magnet, the flux line will flow from north to south. Now, if we have an electromagnet, we will denote it like this. And here also we will have a north pole and south pole. The flux line will flow from north to south outside the magnet, but inside the magnet they will flow from south to north. Thank you.